All right, guys. Hello. I hope you guys are ready to learn about dirt, more specifically harmful dirt, which is a great environmental problem in our global cities. Metal soil contamination in urban areas is caused by natural and anthropogenic sources like pesticides, landfills, even your car leaks, just like how you see this photo right here with the oil leaking from the car. So inhalation, edible crops, and even skin absorption are easy ways of exposing yourself and can be quite harmful to your health if you are exposed to long periods of time. Long periods of exposure can cause adverse health problems, increasing the risk of cancer to organ failure, just to scratch the surface. Children are even at risk of developing lifelong neurological issues, as well as childhood cancer. Um, I haven't even gone to the varieties of metals found in our soils and how destructive they are in comparison, as well as metals like copper, mercury, and cadmium are commonly found in our urban soils. Arsenic is the most harmful metal. If exposed for a small period of time, can be pretty harmful. However, lead is the most concentrated metal in these areas, with an estimated 25,000 parts per million, or roughly 0.4% according to the EPA. So another factor that can take toll on soil contamination is climate change. Researchers have been linking climate change as an enhancer for metal movements in soils to plants. As carbon emissions continue to rise, testing metal mobility in soil has become a focus in environmental management technology. So picking out certain attributes of climate change and testing it out how has come to certain conclusions. For example, natural occurrences in flood and wildfires can conclude that the distribution of metal contaminants. Other hazards like a drought have not been studied enough. So something to combat metal soil contamination has been a unique type of fungus, more specifically avascular mycorrhizal fungi, or AMF for short. So basically, AMF is a type of fungi which is a mutual symbiont with most vascular plants, connecting to the plant roots and working together to provide nutrients, allowing plant growth, and it's increasing its tolerance against outside forces. So this is when the experiment steps in. So this summer I had the opportunity of working in Dr. Ying's Dirty Lab in the environmental science department, working specifically with my mentor on her experiment of assessing microbiomes of mixed metal contaminated sites in arid areas. This being a prolonged experiment with numerous objectives, I would be focusing mainly on identifying the AMF in the brownfield sites and observing what enhances metal uptake and soil properties. So with over 30 samples of contaminated soils in various brownfield sites, each will be tested in numerous scientific methods and measurements such as pH, soil texture and composition, and cation exchange capacity. So like how I said again, with the 30 samples ranging from 3 different brownfield sites, 10 samples coming from each site, we divided them into 2. So 5 of the samples will come from the surface of the soil, and 5 will come from the soil surrounding the roots. So we gathered our samples from numerous places of Southern California. Our first site is in the Santa Ana region, where the soil is usually used for urban agriculture. This region has had big concerns on lead contamination in its soil. So our second spot, we're heading to downtown Los Angeles for our second brownfield site. This community safe space in downtown has numerous metal contaminations in their soil, such as lead, arsenic, and diesel. And in our last stop, south of Glendale, is our Taylor Yard. This big plot of land, aside from the Los Angeles River, has had great concern with lead and cadmium contamination in soil. To have a deeper dive into the metal diversity in the soil, my lovely mentor has had this amazing graph showing the bioavailability of metals in the Taylor yard. She focused mainly on the four metals being arsenic, lead, cadmium, and antimony. She did this by adding chemicals to different soil samples from Site 3, centrifuging it, extracting it, and then running it through a spectrometry to gather all the information. So how you can see right here, focusing on the blue bar, we could see that arsenic is the most bioavailable metal, meaning that arsenic is the most concentrated metal that a plant can absorb in that site. So another way of observing metal mobility in our brownfield sites is the cation exchange capacity, or the CEC. I had the chance of working with this during the summer. So basically, we wanted to see the metal mobility within our 30 samples. We did this by using CEC, which measures the quantity of positively charged ions our sample can hold. Basically, after prepping the soil, I would add barium chloride as a buffer and then run it on the centrifuge. And then after that, we'll observe it on the spectrometry. So here are some pictures during the summer of like me working with the soil and then post extraction. So with this being the early stages of the experiment, we have seen the mobility of in metals in the three contaminated sites, but we'll be aiming on two more objectives. One being to identify AMF in our plant roots and soil samples, and second being to determine which conditions enhance and inhibit AMF remediation. As we understand more about AMF and its properties, AMF can be very beneficial to the environment. Cleaning our soils can be of use in the agriculture industry by providing less contaminated vegetation, as well as reducing the risk of developing adverse health effects. With there being a lack of environmental management techniques, you definitely want to keep an eye on AMF and its future innovations. So other than that, that kind of wraps up my presentation, but I just want to quickly thank the RISE faculty for allowing us transfer students to participate in this program. Very helpful. Also, a quick thank you to all the RISE donors for making this possible. And lastly, a huge thank you to the Dirty Lab for being very welcoming and showing me the ropes. And also Dr. Ying and Karen for holding me down and helping me in all sorts of ways. And lastly, a special thanks to Danielle, my mentor, for allowing me to be part of her her project and helping me throughout the summer. Other than that, if you guys want to talk to us, here's our website and our information for Danielle if you want a more specific overview of the project. Thank you guys.